Welcome everybody to today's talk within the Design++ speaker series provided to you by the Design++ initiative of ETH Zurich. My name is Michael Kraus and I'm happy to be your host today. And it's my special pleasure to also welcome our guest and speaker of today, Dr. Ole Ohlbrock. Before I introduce you to our speaker and his talk, let me shortly provide some background information. The Design Speakers series is a recurring event where we will provide information to upcoming events in due time via our email list, our homepage, and the YouTube channel. You can find all updates on the dates, speakers, and topics also on our homepage. If you want, you can subscribe to our Design++ calendar to automatically import invitations to these events. You're also warmly invited to have a look at our previous presentations, which are hosted on our YouTube channel. I put the link down here on the right-hand side. At the moment, there is a number of professors from architecture, civil engineering, and computer sciences at ETH Zurich involved in the Design++ initiative. For running the business, we are a team of 3 leading postdocs responsible for operating the Immersive Design Lab together with research and teaching activities. A growing number of scientists and chairs are associated to us. So in the case you are interested in the future of connecting AI, machine learning, and extended reality with the AEC industry, just reach out to us. We are more than happy to discuss any ideas or projects with you. Having said all that on the background of Design++ and the speaker series, now let me introduce to you our speaker of today, Dr. Ole Ohlbrock, who is currently still, I think, with Professorship of Structural Design in the Department of Architecture at ETH Zurich and works in parallel in an engineering office, Concept Bronzini in Chur. Ole holds a degree in civil engineering since September 2013. He studied civil engineering with a minor subject architecture at the TU Munich from 2007 to 2013. Between his undergraduate and master's degree, he worked as an intern at Schlaich Bergermann and Partner, each half a year in Stuttgart and New York. In 2020, he obtained a PhD with distinction from ETH Zurich under the supervision of Professor Josef Schwartz. He's currently a postdoctoral researcher and lecturer at the chair of structural design at ETH in Zurich, and his research focuses on the development of computational tools for the conceptual design phase. His research interests are geometry-based methods for structural design, computational modeling of strut-and-tie models, renewable building materials, and structural form finding with machine learning. Please also have a look at his papers and especially his homepage, which I linked here. And all this background information will also be provided to you under the video on our YouTube homepage. So with no further words from my side, I would now hand over to you, Ole, and hear the talk on creativity in computational structural design.
Thank you very much, Michael, and thank you very much also for inviting me to this lecture series. It's a great honor, obviously. And first of all, most of the work that I will show today is teamwork. That's just very important for me to say. I mean, some things have been done by myself, some others in team, but it's very important to state from the very beginning. And actually, Carla and Pierluigi, that are also here, played also an important role in that. Do you see my screen?
Yes,
that's good. So yeah, first of all, good afternoon also from my side. I don't want to say much more what has already been said by Michael. The talk that I want to give you, I gave the title Creativity in Computational Structural Design, and I structured the presentation in 4 different parts. So in the first one, I will very briefly reflect a little bit about creativity. What is creativity? How can it be defined? Then look more into how creativity is usually applied in structural design, then extend it to computational structural design, and then mainly show experiments and share some experience that I made in that field. So to to make it very boring in the beginning, I just brought a few definitions, some quotes, just to give you a little bit of the context of what I understand under creativity. And the very first one, probably you have already read in another talk, is by Edward de Bono, that said that there's no doubt that creativity is the most important human resource of all. Without creativity, there would be no progress, and we would be forever repeating the same pattern. So creativity is usually something very positively connotated. And I think it's clear that we can also not really afford repeating patterns like we did so far. We really go and have to go beyond making things more efficient or just automatizing things. So creativity is really something we urgently need in many different senses, I would say. Another definition that came to my mind during the PhD, or actually right after, is from Günther Abel, and he defined two different concepts of creativity. One is weak creativity, means the combinatorial rearrangement of already existing elements. And the other one, rather, he calls it strong or radical creativity, means transformation, breaking through, replacing old principles, regularities, and laws with new ones. And you will see throughout my talk that I'm actually always somewhere in between the two extremes, I would say. So on the one hand, some of the ideas of my PhD are actually based on the first notion, whereas maybe the way how to look at it, you can also define as more radical. And the last quote in that block, I promise there are not many more, actually also from Edward de Bono, who made this terminology of vertical thinking and lateral thinking, and he describes vertical thinking as analytical and lateral thinking as provocative. And vertical thinking is interested in where an idea comes from, rather the backward use of information, and lateral thinking is interested in where an idea leads to, and this is the forward use of information. And I think all of us in research in particular are also very much, again, in that interface between those two modes of working. And that's also like a nice metaphor for what I did in my PhD, and really trying to use information in the forward sense, speculating, trying to go a step further. So trying to translate now these different definitions of creativity into the world of structural design, which depending on where you ask, would say it's a creative or non-creative field. But the best quote I found is the one of Bill Addis, the most synthetic one, who described how structural design can be done. And he said that the first way is to design structures by making imaginative use of the existing bodies of engineering knowledge and relatively tried and tested structural solutions. On the other hand, many designers believe that the best way to achieve good buildings is to go back to first principles and create designs by a combination of inspiration and logic. So actually what I did in my PhD directly questions a little bit the first approach and rather goes into the second one. But let me first translate these two approaches into more visual understanding. So the first one you could say is an engineer or an engineering approach that uses existing typologies as a starting point for the design. So here we have, for example, a cable stayed bridge and a suspension bridge, and they have a certain logic, a certain way they function. And if we want to design a new bridge, we can use these logic that has already been proven by many existing buildings, and we can start varying and combining these logics and create new bridges. In this case, new cable stayed bridges or new suspension bridges. The problem all of us probably know is that the following one that also De Landa described, that new forms then continue to emerge, but they seem too close to the original ones, as if the space of possible designs which the process explores had been exhausted. So this is in sharp contrast with the incredible combinatorial productivity of natural forms, like the thousands of original architectural designs exhibited by vertebrate or insect bodies. So actually the main idea of my PhD was to take apart, let's say, these typologies, these classifications that are artificial, and break them even further down. So the smallest unit is not an existing typology, an existing reference, but the smallest unit becomes the topology, so the connectivity of elements, and on top of it, the combinatorial force state. So if the force that is transmitted between two nodes is a compression force or a tensile force. And if you take these ones as the smallest module, the smallest unit, and start combining them, you get obviously a much richer playground of solutions. So you can still describe a suspension bridge and a cable state bridge, but obviously you start getting forms that possibly have not a name yet. And if they are structurally informed, like in my research, they are structurally also sound to a certain degree. So that is kind of the translation of this quote by Bill Addis that you see on the left side, let's say more the conventional one that follows a recipe, and on the right side, if you really break it down to the smallest unit, you would rather start with compression and tension forces and combining them. So extending it now even to computational structural design, I really want to quickly do a very personal bracket here. I want to quickly tell you how I approached computation and structural design. So this was my dream as an engineering student, that everything can be quantified, automatized, and optimized. So you, as an engineering student, you have the feeling, but why do the architects not formulate an objective and let an optimization solve the process? And this was really where I kind of came from within my engineering background. And my master thesis in 2013 reflected this very mechanical approach. So I took a station from Zaha Hadid that you see in number 1, the Hungerburgbahn in Innsbruck, and I parameterized it like reverse engineering. So I gave some parameters or parameterized it and gave some degrees of freedom to the design of Zaha, and tried to show how the form could be structurally optimized, and then showed the Pareto optimum in between the design that came from the architect. So the form was kind of ideal versus number 3, where the structure was ideal. And then obviously you can start interpolating between these two extreme solutions. So this was kind of my master thesis in 2013, parametric setup, playing with the parameters, optimizing back and forth. And obviously there was something missing. I mean, typical engineering task you see on the very left. So you get a given form, you optimize it, you make an analysis, and you optimize the cross section. In my master thesis, I was actually somewhere in the middle. So I started to interact with the form. So I gave the form, I questioned the form of the architect and produced different variations. But actually it's clear that in the design process, you have to cover all the 3 different dimensions. So actually it was very important for me also to capture the topology, as we have seen already before. So in that case, I really wanted to, after my master thesis, also to enter the realm of topology, so to say. And then I was also very lucky that I came to ETH, to this chair where I'm sitting right now, where it's very important that we're not so much only interested in an analysis of the forces. So you have a given form, but actually you really want to use the force as a design principle, as a starting point for the design. And that was like a nice coincidence for me that some of these things came together, the interest in computation, in form finding, in playing with the topology, and all these things actually matched very well to the interest of the chair, which is graphic statics and strut-and-tie models. So to really control the force flow in a synthetic way. And that is the research that I actually developed here at the chair together with colleagues. It's called combinatorial equilibrium modeling. Combinatorial because, as you have seen already in some of the slides before, it's about combining forces in space. And yeah, so on the one hand, it will allow you, let me show this one. On the left, you see then a form diagram, a structure that is representing the form of the structure. On the right side, the force diagram. And you will be able to really explore different solutions in real time. So you're not in this feedback loop that you press a button and you wait. But ideally, you can really interact between those two different realms, form and forces. And as I have said, the importance of topology and combinatorial was also very important. So ideally, my research opened up a playground in which you can, on the one hand, explore the topology, so you can start manipulating the connectivity, but also compression tension. And then on the vertical axis, actually you also have the possibility to explore different metric solutions that fulfill different constraints, for example. So again, here we have a little bit this connection to lateral and vertical thinking. On the one hand, you have this lateral exploring mode, but then you have this vertical mode in which you maybe look for specific solutions once you have objectives, once you have clear constraints. So this was like the starting point for my PhD. Here we see some technical peculiarities of the algorithm. So there are form finding techniques that can provide structures in equilibrium, but at the end of the process, you will have an equilibrium state, whereas the method that I developed, like force density method, ensures that you will always have something in structural equilibrium. So this is conceptually sometimes an advantage, because everything you see on your screen structurally has a certain value. And then obviously, if you have additional constraints, you need to also activate iterative procedures. So yeah, with the help of, as I said, of colleagues, we developed also tools. This was the first release we did together with Pierluigi 1.5 years ago, a small grasshopper script. Now, Rafael Pastrana, who is now in Princeton, actually developed the Compass CM version. Very, very impressive what he did, and also extended it, or improved it, much nicer the way he scripted it, but also using automatic differentiation inside to speed up the optimization procedure. Here you see a very small script that we used with students in our class here at ETH, architectural students, to design very quickly some small pedestrian footbridges. Yeah, very, very easy to use if the tool is properly introduced. Before I go more into, let's say, data-driven approaches, I quickly show some manual, more top-down experiments. So here, that is very conventionally how I used it in my PhD for the design of pedestrian bridges. So it is mainly like translating sketches into a proper form-finding result where you get the precise geometry. We also used it in a real competition. The competition actually was done and won without us, but then the architect and engineer contacted us and asked us if we could define the proper geometry of this curved bridge, and we helped them. This is a bridge between Spain and Portugal, 300 meters long, and it will be built next year, if I'm not completely wrong. And yeah, obviously you can apply this very same method and tool for very different contexts. Here we explored some different shell typologies. What happens if you start combining compression and tension in a shell structure and start playing with the parameters? Or also here, a master thesis by Davide Tanadini, who's now a colleague, that designed these towers not by actively manipulating the geometry, but really by precisely playing with the forces. And out of this force constellation, actually, he managed to get this very rich diversity of shapes. Large span roofs are also very nicely a nice, let's say, building typology in which you can apply these form finding techniques. This was a stadium competition we did together with Pierluigi and Lukas Ingold in 2016. But obviously it was also always the idea of us here at the chair that we're interface between architecture and engineering. How can we apply these methods also to more, let's say, conventional architectural questions, so multi-story buildings? And you see that if you start activating, for example, forces within the slab, you can start make the columns take certain shapes, create certain spatial arrangements. You can start to create column-free spaces and so on. And this is a very powerful way of looking at architecture and engineering at the same time. So these models here are not very detailed, but they reflect from the very first moment how the loads will be transferred within the building, and can give very nice ideas in which direction to go. So yeah, I mean, now we have this algorithm, this plugin that can very quickly generate equilibrium models. And at some point it was clear that we wanted to open the box of Pandora, kind of. So one of the first examples, to continue with the same context, was to think of an automatic building generator. So you have certain things that can be varied. So for example, number of floors, number of floor heights, different patterns. And if you let this run very quickly, you can very quickly generate very different building schemes, where the structure load transfer is controlled from the very beginning. You get different criteria, you can pick one, and then obviously you also get other performance criteria like daylight or lateral stability and so on. And what is quite nice is that you, from the very first moment, you kind of now create floor plans through a structural pattern, which is a bit maybe also questionable, because most of the architects don't want to give away the control of the spatial arrangement. But nevertheless, it was a very interesting experiment to do. And you see that all of a sudden you can create buildings where the walls not necessarily have to stand on top of each other, but the building as a whole is still making sense. And you create these very beautiful open floor plans. Yes. So as I've said, now I want to come more to the experiment section, and in that regard also look into more aspects that are, I guess, closer to the Design++ initiative. And in that case, we have this dilemma that I already mentioned, that on the one hand, we're now having very powerful mathematical tools and scripts and algorithms, but architectural design can rarely be stated with explicit objective functions, and therefore is open to be optimized in a traditional sense. The evaluation criteria and the design objectives often co-evolve with the development of a project. So far, very often, computation is very powerful in a very narrow setup. You can optimize if you have a very clear idea of where you want to go, but in a very early design stage, in which I'm particularly interested, it's still very difficult to apply conventional optimization. The other extreme would be to say, okay, we can generate a lot of different solutions, and now we present each individual in a large population at each generation to the designer, but this very likely will not make sense either, because the designer will get very tired, and I mean, he cannot look at 10,000 different solutions. So this was the main starting point for our investigation and our collaboration with Vahid and Carla. This is a slide I have borrowed from Vahid, who I took some classes about machine learning some years ago. And in our first attempt, we actually looked into unsupervised learning to overcome this problem of not running directly into optimization, but also not directly looking at all the 10,000 different solutions that we can generate in a short number of time. So in that regard, the very first experiment we did with a master thesis with Lukas Furiman in 2018, in which we used the tool that we developed to generate 250,000 solutions, and we filtered them, accepted only 36,000, and then we used clustering techniques to present the essence of the solution space. In this case, we used self-organizing map in UMAP, and we were able to condense the solution space. So here you see some of the best matching units. You see different solution spaces. You see different clusters emerging in that big solution space. Here, in that case, the topology we kept constant. So even though the shapes look very different, the topology is the same, only compression and tension and the metric values were changed, but the topology we kept constant. And then obviously it was the question, yeah, but we want to open up, we want to compare topologies that are very different from each other. And in the beginning, obviously one of the struggles, if you have a discrete network, you have a certain vector in which you store information, but if you have a different topology, different number of nodes, the vector length is also different. And this is where we had really some long discussions and many experiments and tests with Luca's master thesis, where we then try to condense some of the topological information into an image, representing the connectivity, for example, as an image. And to be honest, it kind of worked, but on the other hand, opening up the topology also created, as you see, some very noisy and in let's say in a conventional design world, a bit chaotic solution. So we were not really sure that we're on an interesting path here. Here is just some fancy 90 years image that looks like a disco from the 90s. Another example that we tested here was the self-stress stadium wheels. So just to show you some different experiments that we did. And in that case, we produced a lot of different solutions, again, keeping the topology the same, but explore richness of solutions within the same topology. So all these wheels are self-stressed, like a bicycle wheel or a roof for a baseball or football stadium. And again, we used the same ideas as before. At some point, we had the idea also with Vahid not only to cluster the different solutions, not only based on mean values or absolute values, but also to introduce higher order statistics. So to have a more closer look at the distribution of the different parameters within the solution to get a more precise overview. Yeah, here you see, for example, a self-organizing map with a certain resolution. And then obviously it's at the end always a question on how much information, visual information you can also capture and digest, I would say, because we can still not really, I mean, yeah, it's very subjective and personal, I would say, how you can operate and interact with these maps. Yeah, here a last step within that project thesis or master thesis in 2019. So yeah, the second phase, I would say, of our experiments actually was, how can we now bring back the feedback of the designer? So in that first phase, we generated 1,000 different solutions. We used the self-organizing map to cluster the solutions to get more an essence of the solution space, so don't have to look at each solution, and we also don't have to optimize because we don't know the objective yet. So in that case, actually, we worked together again with Carla and Vahid and Pierluigi, and we borrowed this framework, or this very standardized framework, from a work of Rivka Oxman, where you usually have in a design process, or also in a computational design process, at some point a generative step in which you generate different solutions, different alternatives. You have a quantitative evaluation and filtering. So you can directly discard, for whatever reasons, a certain percentage of solution. Then you have a clustering, possibly. And then at some point, there will be also a qualitative evaluation. And all these steps can either be performed by a human or by a machine. I mean, this is really, at the end, open to discussion. Very classically, the human is probably the one that is the best in step D. But I mean, as I said, it's a very generic definition of a computational design process. And then obviously, once you have the designer or the machine has selected something, you can also start regenerating the solutions that are promising and enter this iterative process and connect the different steps as you want. So here we went again into the context of a design stadium roof. We produce a lot of different solutions. We filtered them, we clustered the solution space, we tried to shrink it down. In that case, we had 14,000 solution. And then in that case, we had 3 human designers that actually made a distinction and make the checkbox, which are the designs we actually want to keep and which are the ones we want to discard. And based on this classification, in that case, yeah, Carla can explain it better than I. We use gradient boosted tree to regenerate new solutions with the premise that we will have more successful candidates in the second run. And here you see a little bit the overview of the different steps and also how long they took. So for the generation of 35,000 alternatives, it took the computer 2 hours to generate them. The quantitative evaluation, also making all the statistical treatments, it took 8 minutes, and then the clustering 17 seconds. The qualitative evaluation, as I've mentioned, was done by humans in that case. It took us each 15 minutes. There was again a regeneration and then a final selection. And at the right, you see very schematically some ideas that came out of this design process. So this was a very nice collaboration with Carla. It took us also, I think, a lot of time to write the paper about it, but we learned a lot on the way. And then obviously afterwards, we had also the idea to extend now what we have learned to other disciplines. So in that case here, together with Federico, who's another colleague of mine, we applied more or less the same workflow to the design of facades that are, on the one hand, providing the structure. So the force transfer, they're not only carrying their self-weight, but they're also carrying parts of the slab. And these skeletons ideally can also serve as a solar shading device. I mean, even if they're very narrow in that case, but you will see later on that you can also use them. That's actually the PhD topic of Federico, to activate the structure, also becoming a passive shading device. And you see that you can obviously enrich the information that you capture in your vectors, not only about, you don't only capture structural performance criteria, but you can also put in there other performance criteria like the solar radiation map and so on. So this was one test we did, and then we actually tried to go a little bit more crazy. So we took a reference of the Christian Carrett's design competition for Swiss Re some years ago. And here again, a little bit the workflow behind. So there is a certain input. We translate it into a first form. This form we can materialize, give different thicknesses and so on. We can do a secondary structural analysis to check other effects that are not captured in the form finding. We can do solar analysis in that case with Ladybug, and we put everything in a vector. And this vector we then actually used SumPy libraries to do the clustering and the rest of the process within a Jupyter notebook. And here you see some interesting results. I mean, again, you can argue that at the end the designer sees eventually surprising results, not only in terms of the formal aspect, but also in the way the structure and the solar shading performs. And this is obviously one of the main arguments at the moment to use also computation, that you can increase the decision making, you can improve the decision making, and to give a designer more information as synthetic as possible at his hand. And yeah, the last one that we actually also want to show here is we used more or less again the same principles in the context of reusing elements. I mean, here we work together with Jan Brütting, who's an expert in reusing structure elements, and we used again this CM to do the form finding. We used on the way in between some stock assignment algorithms to optimize the assignment process or to minimize the greenhouse gas. But at the end, it's always about variety, about showing a designer different options, but also showing him the consequences behind in terms of quantity. And I think this is actually what we are trying to do here. So yeah, my personal observations in that field, within data modeling in the context of early stage structural design. So most of the data that we were looking at is actually self-generated. So we were not looking at existing bridges and then extracting something, but we took, as you've seen, always this form finding engine as a starting point to produce different solutions. And usually a top-down inspired process often leads to very predictable and self-similar designs. So you can really use it to narrow down to find a specific solution. On the other hand, a bottom-up process in which you keep everything open and you make more a rule-based process leads very often to very chaotic and noisy solutions that very often are not useful in an overall context. And that is a bit the dilemma that I think I was confronted very often, that we had many discussions. On the one hand, we wanted to also see something, let's say, new or surprising, but on the other hand, also it should look to a certain degree meaningful. And if you not describe the geometry, but describe the structural logic, you have actually another layer in between that you have to pre-think. And this is what I wrote in the second sentence, that actually brain work and also creativity is needed to formulate, to parameterize the problem in order to get many meaningful yet diverse solutions, which then also can be interpolated. And here, one of the questions that I also have is if this actually is always case sensitive, this parameterization, or if there is maybe a way also to make it more general. So it's very challenging to find a balance between chaos and positive surprise in that field of that I was working in the last years. And yeah, I mean, now to maybe end again with a quote that is a bit provocative in that sense, or in that context here, is that data does not by itself generate ideas. It usually does not even suggest them. It is useless to believe that creative effort can be replaced by a careful accumulation of data. If ideas are needed, more data is no substitute. So I think it's very important that we keep on asking the right questions and not only believing that data by itself can kind of solve bigger problems and also lead us the way. I think, I mean, you're all very experienced in also and careful, I guess, in that sense. But this is an old quote, very maybe also how do you say überholt. Yeah, maybe it's not valid anymore, but I found it, and I think I just had to show it here because for me there's a certain essence in it. And yeah, that's actually the part of mine. I think I have not more slides to show, and I'm very happy to open the discussion with all of you. And if you have questions or feedback, I'm glad to hear it.
Cool. Yeah, very nice, Ole. Thanks for the nice presentation. So I will thank you, Ole, for this interesting talk and the discussion. Your time and efforts are very much appreciated. As I said before, we will upload information of this talk together with the video on our YouTube homepage. Yeah, with this talk, we come to the end of this cyclus of our seminar series in the fall semester. On behalf of the whole Design++ team, I wish you all a Merry Christmas and a Happy New Year. Stay safe and see you next year for a new round of talks within this seminar series.